I've actually just some sort of feedback on the homework sessions. I've actually just learned like a lot from just doing every single exercise and even going through those concepts, seeing how the author answers a lot of those questions, not with just like a single item answer, but actually expanding that into different scenarios and you know, under this scenario it'd be that situation, under that scenario it'd be that situation. So yeah, I actually just has been quite beneficial to me as well, a lot. So
same over here.
yeah, cool. So let's get started. I know some of you were probably like me, a little bit overwhelmed by all that mathematics that came with support vector machines. So I still want to kind of just, I want to share something that was, that I came across. I think someone sent this support vector machines in the channel already. I think it was Shamsuddin. But like actually he or Josh from StatsQuest actually went into different kernels as well, the polynomial kernel and also the radial basis function kernel. So and they're really good, so I highly recommend it to watch those. So cool. Back to the homework. So I want to kind of separate the homework session as we did for chapter 4 into basically the conceptual questions and also the coding questions differently. And so from 1 through 7 is basically the concept questions, and we'll just go through them, each of them one by one, and I'll basically just ask you guys questions, and you guys can give me answers, and different people, you know, feel free to just jump in. And we'll probably spend some time on each of the 8, 9, 10 question. Then we can kind of just spend a little time coding that, or even just, if you don't want to do coding, even just like literally understanding the solutions and trying to replicate it a little bit on your own. I think you could still learn a ton just by doing that, because, you know, then you will know what the best practice is by the author's methods or approach. Cool. So let's start with number 1. What is the fundamental idea behind SVM or support vector machines? Basically, you know, describes SVM. Anyone wants to take that?
It's to find the widest street possible between two class. If you're doing it for a 2-class problem, for example, you want to find the widest street possible between the 2 classes.
Right. And let me just ask a follow-up question. What would be the soft margin, and what would be the hard margin classifier? Anyone wants to answer?
Okay, the hard margin is when you require that every point be correctly classified in its class, and you don't allow any violations. That is, I guess I should say that every point be outside the margin in its class. So it doesn't even allow, I think it doesn't even allow points to be to cross the margin, even if they are on the right side of the decision line.
Mm-hmm. Mm-hmm.
And then the soft margin is where you allow a certain amount of violation you allow points, you allow a certain amount of violation, which you get it gets included in a regularizing term that gets added to the loss function. So you penalize for violation, but you don't forbid it.
Yeah, absolutely. And let me just kind of go through the answer by just, I guess I'm just going to read it. I think you're definitely right. So the fundamental idea behind SVM is to fit the widest possible street between the classes. In other words, the goal is to have the largest possible margin between the decision boundary that separates the two classes and training instances. When performing soft margin classification, the SVM searches for compromise between perfectly separating the two classes and having the widest possible street. A few instances might end up on the street. Another key idea is to use kernels when training on nonlinear data sets. And I think, as I just said, some of the most commonly used kernels would include polynomial and Gaussian RBF. Cool. Number 2, what is a support vector? I mean, feel free to go back and literally go through some of the pages and find the concepts. It's still a good review process if you find that, right? So
Come on, ladies and gentlemen, you guys know this stuff. Speak up. I know there are lots of people that know this.
Putting it in the most simplest of terms, right? So this is coming from the finance world. This is the mean variance efficiency boundary idea. So a support vector would be something where it's the margin. It's what classifies. That's not even the simplest way to put it either.
It's a data point, right?
Right.
And there's something special about the data points that are called support vectors. Right? So you sort of started to say the answer, Mosh. You talked about margins.
Right.
And so, yeah.
It's the one, well, so it is the margin. It's those points that sit between two different classifications, but right in mean variance efficiency, it's the boundary where that's the best optimal portfolio given all the different mixes of financial products. So this is that boundary, all the points that make up the boundary at different no, that does.
Yeah, that's right. I mean, so when we look at these support vector machine, when we see the drawings, we see a line which is a hard decision line, but there's always two dotted lines, one on each side at equal distances, and those are the margins. And so what you're saying is that the support vectors are the points, the data points that actually lie on those margins.
Yes.
Yeah, so I'm showing exactly that, right? So these, the green dot here and the red dot here, they determine the support vectors because they're right on the edge. And
it turns out that all the data points beyond on the other side of the margin, that is on the upper side of the upper blue margin and on the lower side of the lower blue margin, all the other data points don't even matter once you know the support vectors. In terms of in other words, if you added more data points to the data set that were outside of those two margins, they wouldn't even influence the answer.
Right.
Because, what does that, could you elaborate on that, Joseph? Sorry, Wanchan. When you say it doesn't, any other point doesn't matter, what does that exactly mean? So so the support vector here in Winchang's diagram, is that the blue line?
The blue lines are the margins, right? The two blue dotted lines are the margins. And what I'm saying is that if you add any points to the data set that are outside of those margins, that is above the upper blue margin or below the lower blue margin, those new data points don't even influence the decision boundary. It won't change.
Yeah. Got it now.
Yeah, and you can read more on that on page 154 if you have the book. It says, notice that adding more training instances off the street would not affect the decision boundary at all. It's fully determined or supported by the instances located on the edge of the street. These instances are called the support vectors. So basically the instances that are located on the edge of the dotted lines, those are called support vectors. Right, so on page 154 if you want to read more into it. Okay.
Now, I like the way he uses the term edge of the street instead of margin. So, you know, that he's talking about those dotted lines, which are called the margins in technical jargon, but in his jargon, they're the edges of the street. And the support vectors are those data points that lie on those street boundaries, on the edge boundaries.
Yeah, and you see this green dot and red dot, they're right on the edge, right? So yeah, so those are actually support vectors. Okay. Number 3, why is it important to scale the inputs when using SVM?
Isn't it the case that all vectors that lie even within the margin are for soft classification support vectors, not just the ones that lie on the margin? That's what I thought I mentioned last time we discussed this as well. He says that, I believe, in the answers. It's everything that lies on and within.
Okay, so for hard margins, it's just everything that lies on the street boundaries, but for soft margin, it's everything that lies on or within the street.
Yeah, that's my understanding, but I think it would be good to clarify.
Yeah.
Okay. All right. I'll probably look into it, see where he actually says that. But specifically support vectors, I mean, on 154, that's kind of how he defined it. Do you know where he mentioned that on the book?
I think in the Appendix A, where he gives the answers to the questions, I believe he explicitly says that it's
okay, well, let me read the answer actually. So after training an SVM, a support vector is any instances located on the streets, including its border. The decision boundary is entirely determined by the support vectors. Any instance that's not a support vector, i.e. is off the street, has no influence whatsoever. You could remove them, add more instances, or move them around, and as long as they stay off the street, they won't affect the decision boundary. Computing the predictions only involves the support vectors, not the whole training set. I think the last sentence is actually pretty key, pretty important. Computing the predictions only involves the support vectors, not the whole training set.
So it's what Srinivas said. Then it's all the data points that are either on the margins or on the street.
Yeah, it's basically on the street, including its border.
Right.
Those are the support vectors. Yeah.
And that's if you allow the margin violations, because otherwise there won't be any on the street. There will only be points on the borders.
Yeah. So basically, it's saying this red dot. It's even though it's within the margin, but it's on the street, and it's it's taken into account when it calculates the prediction, and also it would be considered as a support vector as well.
Yeah.
Yeah.
And by the way, the pronouncement that data points that are off the street don't influence the decision boundary is not obvious. It's just it's a statement of fact, but we haven't proven it. It'd be interesting to understand it would be interesting to understand why it's true.
Got it. Cool. All right. Any other one has any questions or points to be made on this one? Okay. Number 3, why is it important to scale the inputs when using SVMs?
Because you want those decision boundary lines to not explode if certain measures are just different. One column of data is in fractions, other column of data is in thousands.
Yeah, I think you're absolutely right on. Otherwise, I think as the answer said, basically, if the training set is not scaled, the SVM will tend to neglect small features because it's actually trying to fit the largest possible street. So if it's really small and basically it's way farther off the street, and it will probably just get neglected, but it might still be important data points.
Can I build on that question to the group? What are the best ways to scale data sets, data? Say you have, in fact, I've got one data set right now that I work with, and I had 300 columns of data that are different orientations of something, and they are all numerical. If I wanted to scale them and wanted to scale all 300 columns, is there a specific way that certain folks here have tried that's just a little different, unusual experience they've gained?
The usual way is to use standard scalar in sklearn, which does nothing more than subtract the mean for each column. You subtract the mean and then divide by the standard deviation. That puts all the scales on the same footing.
Yeah. Simple enough. You just call it standard scalar, a scalar dot, and so on. Is there any other way that folks?
Well, there's other ways that I've heard of. One is Minimax, where you take the minimum and maximum and map those to be 0 and 1, and everything in between mapped accordingly, scaled accordingly.
I mentioned this previously. So this page actually plots all the scaling methods. And let me share that let me just type that into the chat. So this actually plots the effects of scaling. Like if your original data looks like this, standard scalar would actually, basically, if the median income ranges from this to that, and after the standard scalar, it would just be like this. And Minimax scalar would look a lot smaller in terms of the range. And you can see the description too. Standard scalar removes the mean and scales the data to unit variance, which is, I think it's just standard deviation 1. However, the outliers have an influence when computing the empirical mean and standard deviation when shrinking the range of features values. So standard scalar therefore cannot guarantee balanced features in the presence of outliers. So you want to keep in mind of that, like in terms of choosing standard scalar as your scalar. And here, like Minimax scalar is actually very sensitive to the presence of outliers. So you want to be mindful about that as well. And there are a bunch of other scalars, robust scalar. I've seen people using this before.
The Boxcox transforms, which are pretty common, right below power transforms. That's pretty common in biomedical. Huh.
Yeah, I guess the Boxcox transform takes some weird distribution and maps it so that it's closer to being Gaussian.
Yep.
This one?
No,
One-tile transform?
go up a little. This one.
Power transformer.
Mm-hmm.
Okay. Boxcox. Okay.
Thank you. I'm going to forward this page to this funny, odd little startup that's been focused on this problem for literally 3 years.
Cool.
So which are the factors that dictates which transformer that we use here, or which we will use here? Which are the factors that dictates that?
So, sorry, I didn't hear the question. What were you saying?
Yeah, the question is, as we are seeing here, there are several kinds of scalar here. So depending on which factor do we decide which one to use?
Yeah, I think one of the factors, as it said, is outliers, presence of outliers.
Right.
So Minimax scalars actually, and both of these scalars are quite sensitive to presence of outliers. So you want to be conscious of that.
Mm-hmm.
So the first thing you do is you do a histogram of the columns and see what they look like. Are they close to being Gaussian? If they are, then just use standard scalar. If they have a lot of outliers, if they're fat tail distributions, then you might choose one of the other ones that they recommend.
Yeah, right here, a robust scalar. Unlike the previous scalars, the center and the scaling statistic of this scalar are based on percentiles and are therefore not influenced by a few number of very large marginal outliers. So this one is more, well, I guess hence the name, robust. And so it's more robust against outliers, a few of them, yeah.
So it seems like most of the things are being dictated by the outlier, whether it's there or not.
Well, that's why you're scaling, right? So you're trying to squash all your data points into some sort of range with some sort of a statistical characteristics. So, yeah.
Okay.
Yeah, but let me just also make a point. I was just checking. Let me see if I have batch norm here. Hold on. Sorry, let me just stop sharing. I just want to talk about batch norm because that's also one of the scaling, one of the ways, I guess the probably most important way to scale for neural networks. So let me just talk, since we're talking about scaling. So, so this is batch norm. Well, actually, this is, you normalize output from activation function with a sort of a standard scalar, and you multiply normalized output by arbitrary parameter G, which is trainable, and you add arbitrary parameter B to result in product, and that B is also scalable, trainable. So, and that's actually the way right now, and that's, I think, how FastAI implements it as well. Basically, when you have a layer, like could be a conv layer, convolutional layer, then you apply the activations out of that conv layer to batch norm. Then after that, you apply the activation function. Well, actually, you do that after the activation function. Sorry. So, as it says here, yeah. So,
And the B and the G are parameters in the model. Are they different for every batch, or are they the same for the entire data set?
I'm not 100% sure, but I'm guessing they're different. Anyone knows the answer? Oh, okay. So I actually made a note. FastAI does batch norm before activation function, but some do it after activation function. So
I think the B and G are learned just like the weights. So at the end of the training, you get good values for B and G, and then you use that for your prediction.
That's for the whole. So B and G, one value are fitted for the entire data set, not one value for every batch. That's what you're saying, right?
I think it's for every batch. If you look at the layer structure of FastAI, how it's built, it's actually you apply a batch norm for every single layer.
Yeah, but you don't have to solve for the B. You don't necessarily have to solve for the B and G at every, every time you normalize a batch. They could be, and I think what Gautam is saying is that they are, there's just one G parameter and one B parameter that are solved for the whole data set.
Well, it's like weights, right? So
yeah.
Okay. If that's what you meant, yes. Yeah.
Also, even if you're using batch normalization, you would still have to normalize the data that you put into the neural net, right? By standard scalar or whatever. It doesn't matter. You would.
Yeah, that's the first step, right? That's the first step in the notes that that Wencheng is showing.
Wherever you have a distance matrix, it's always good to normalize the data just to weed out the random effects.
Okay. Okay. Let's keep going. Let me just stop sharing. Okay. Let's keep going. So, number 4, can an SVM classifier outputs a confidence score when it classifies an instance? What about a probability? I think we've probably touched upon this when we did chapter 3, when we did like SGD classifier, if you guys remember that. And when we try to kind of just see the thresholds, and if you remember, and we output a bunch of confidence scores.
Sorry, but I don't see your screen. Am I the only one? Or?
Sorry, I couldn't hear you.
I'm not able to see your screen.
Yeah, I'm not sharing anything right now. I'm just going through the problem. Yeah.
So for number 4, the support vector machines method does not provide a probability, but I think people have written methods that you can use on top of it that can convert the data points to probabilities, or can get probabilities for the classes.
Actually, in the SVM, I was going through the chapter number 7 or 8, I guess, the random forest chapter. So there they are coming up with this voting classifier. So during that, they are taking SVM as one of the classifiers. Some other like linear regression, etc., logistic regression, etc., are there.
Right.
So SVM is also there. In that case, what they are saying, this particular thing, that when you are coming up with a voting classifier, you need to what is this? The soft voting classifier, most probably the name is. You need to come up with a classifier which has the probability as output. So in that case, what they're saying is that for the SVM, generally, it does not output a probability. But if you include one parameter, I am forgetting the parameter name, you make the parameter name as true. In that case, the SVM also provides the predict probe method, which is the probability output.
Does it? Does it? So you can show us the page on the scikit-learn that tells you how to get a probability out.
Sure, I'm sharing the screen.
Because what you're talking about is a little different. It's an ensembling. It's an ensembling method. When you take a bunch of classifiers and then you decide the class by voting, that calculates a probability by just the fraction of votes that each class gets, that's the probability that it assigns. And so the participating classifiers don't have to have a predict proba output. They just have to vote one way or the other. And then if you have 1,000, if you have like 1,000 different models and you're averaging them together, and 900 of them give you a of class 1 and the other 100 give you a class 2, then the probability that this point will be, the probability of class 1 is 90%, or yeah, but I guess what we're looking for is the place in scikit-learn where we get the predict proba out of SVM.
Yeah, this is the portion that I'm talking about.
Okay.
There, you can see our screen, see my screen, right? So here for the voting classified section, this is the code that they're coming up with. So this is the three classified that they make use of. In the SVC portion, you can see here they are saying this is the first portion. Let me take you to the code. It is better to take a look at the code actually. So this is the code, and inside that you can see here this for the hard voting classifier. This is the voting hard. So here what they are doing for the linear SVC, they are taking the SVC gamma scale, the standard of the shell parameter. That's fine, and this is for the hard voting classifier. Now when they come up with the soft voting classifier, then they, along with the other parameter, they make probability.
I see. So it can give a predict proba output.
Right.
Okay.
So here they're mentioning that where is the portion? This one, I think. If all classifiers are able to estimate class probability, that is, they all have a predict proba method. Then you can tell scikit-learn to predict the class with the highest class probability, averaged over all the individual classifiers. This is called soft voting. So it often achieves higher performance. Blah blah. All you need to do is replace voting is equal to hard with voting is equal to soft, and ensure that all the classifier can estimate class probability. This is not the case for SVC class by default, so you need to set its probability parameter to true. This will make the SVC class cross validation blah blah, and it will add a predict proba method.
Thank you. That's great. I did not know that.
Yeah, so Joseph, it does what we discussed, I think, last time, which is to throw a logistic regression on top of SVC to give the probabilities.
Right, and it does it by measuring the distance. I think it does it in some way by measuring the distance of each point from the margin. Yeah. Points that are farther away from the margin on the correct side are given high probability, and points that are close to the margin or on the other side of it are given low probability.
Yeah, so it inherently doesn't, but it can be made to generate it by adding that flag.
Yeah.
The method you were saying, that is exactly what is employed here, like throwing a logistic regression on top of SVC. That's how it works.
Yeah, that's what I believe.
Yeah, so that's definitely right, as the answer says. So let me just read it. An SVM classifier can output the distance between the test instance and the decision boundary, and you can use this as a confidence score, which we did in chapter 3, right? And we use those confidence scores to treat them as a kind of a proxy for threshold, and to kind of tweak the threshold for precision F1 scores and so on and so forth. However, this score cannot be directly converted into an estimation of the class probability. If you set probability equals true when creating an SVM in scikit-learn, then after training it, it will calibrate the probabilities using logistic regression on the SVM scores, parenthesis, trained by an additional 5-fold cross-validation on the training data, close parenthesis. This will add the predict proba function and predict log proba function methods to the SVM. Did I explain it all? Cool. Anyone else wants to make a point or has a question on this? Okay, no, great. Number 5, should you use the primal or the due form of the SVM problem to train a model on a training set with millions of instances and hundreds of features? Anyone?
Okay, remember the dual form is what he says is a good idea when you're dealing with with a a problem that has more features than instances, than data points, right? So that would have what would, I think somebody referred to this as a fat matrix, a fat matrix, a fat design matrix, whereas this problem has a very skinny design matrix, right? It has millions of rows and hundreds of columns. And this is the case where you're way over determined. You have many more data points than parameters, and so you're fine using the primal form of the support vector machines.
So I think on page 169, he actually mentioned perhaps part of the answer. The do problem is faster to solve than the primal one when the number of training instances is smaller than the number of features. So more importantly, the do problem marks the kernel trick possible, makes the kernel trick possible, while the primal does not. Okay, so basically, do problem is faster when the number of training instances is smaller than the number of features. And in this case, we have...
Pancake, so you're saying when M, the number of instances is less than the number of features, then the dual is preferred or is faster, correct?
Yes.
Well, the number of training instances is smaller. Yeah, exactly. Smaller than the number of features.
So it's the opposite, Joseph, of what you said?
No, it's the same as what I said. If you have a fat design matrix where the number of instances is smaller than the number of features, then the dual method is faster. But if you have, but if you have a thin design matrix, a skinny design matrix where the design matrix is number of instances by number of features, right? And so if you have a million instances and 100 features, then it's a skinny design matrix, and that makes the primal method faster. But I only gave, according to what Wenchang reminded us here, I only gave half the answer. The other half is, do you need the kernel trick or not? And if you need to use the kernel trick, then you have to use the, you just have to bite the bullet and use the dual method, even though it's slower.
Yeah. Okay, so let me read the answer. This question applies only to linear SVMs, since kernelized SVMs can only use the do form. So that's exactly what Joseph and I touched upon, and also what the book says on page 169, right? So it's actually not applicable to a kernelized SVM because you can only use do form. The computational complexity of the primal form of the SVM problem is proportional to the number of training instances M, while the computational complexity of the dual form is proportional to a number between M squared and M cubic. So if there are millions of instances, you should definitely use the primal form because the do form will be much too slow. So the primal form is M, right? So but the do form is M between M squared and M cubic.
But if you have a very nonlinear problem and you need to use the kernel trick, then you have to, you can try to use the dual. I mean, you should try to use the dual method, try to implement the kernel trick, and see if you have enough compute power to do it. And if not, you're stuck with using the primal kernel with a linear. The primal form with the linear kernel.
So when we are actually in practicality applying all these things using the library and all, so how does we make sure that which form are we using? Is it that whenever we use linear SVC or SVM with kernel linear, then by default it is using the primal form, and whenever we are using the kernelized SVM, it is using the dual form? Is it like that?
If you need to use the kernel trick, then you have to use the dual form. That's what it is.
Yeah.
Right. So I am, whether which form I am using, that is not up to me. So whatever library I use, whichever it uses by default, that's what decides it.
You don't have a choice between linear. You don't have a choice of kernel.
No, I'm talking this regarding the primal form and the dual form. It is not up to me which form I'm going to use. Whichever library I decide to use, whichever form it automatically uses, that's what I'm bound to.
Oh, you have a library that decides automatically which form, whether to
No,
use the
that is,
primal or dual form?
yeah, that is my question actually. So is it like that whenever we use linear SVC class, then by default it is using the primal form. And whenever we use SVM with kernel is equal to, let's say, poly or something like that, it is by default using the dual form. Is it like this?
Yes.
Mm-hmm. Okay.
So in other words, if you have millions of instances and not too many columns, and if your data set is highly non-linear, so you should probably not even use SVM, because you have to use kernelized SVM, but like the do form is way too slow.
Yeah.
So you're screwed in that
Good
case.
answer. Good
Yeah.
answer, Wencheng.
Yeah. So, okay. Number 6. Say you've trained an SVM classifier with a RBF kernel, but it seems to underfit the training sets. Should you increase or decrease gamma? What about C? So when you're underfitting, should you increase gamma or decrease?
I think we should increase C and it default decreases gamma. That's what one of the two of the pictures show that, I think.
Sorry, what was the answer you said?
Yeah, I think we should increase C and decrease gamma. I remember seeing one picture which actually talks about this one.
Yeah,
Trying
which
to
one?
yes, you can. No, it seems the other way around. If you see the picture 511,
511? Yeah.
there it
We
shows
sort
that.
of, sorry, we sort of need to underfit. If we need to underfit, we probably need to increase the C. That in turn decreases the gamma value. So I'm sort of allowing more features to be wrongly classified.
Yeah.
Does that make
So yeah, so I mean that's I think someone else said it correctly. You should increase gamma or C when you're underfitting, and decrease gamma or C when you overfitting.
I think gamma and
Let's remember what gamma and C do. Gamma controls the width of the Gaussian, and if you're underfitting, that means your Gaussian is too wide. So you need to sharpen it. You need to make it sharper. And the parameter that controls the sharpness of the Gaussian is gamma. And gamma is proportional to 1 over sigma squared. Remember the Gaussian is e to the minus x squared is proportional to e to the minus x squared over 2 sigma squared. And sigma is the width of the distribution. So if you want a sharp Gaussian, you need sigma to be small, and the standard deviation of the data to be small. That means that gamma has to be large. So that's how to reason to what you do with gamma. Now, as far as C goes, I forget. So C allows you to be allows more margin violations or less margin violations. When you increase C, are you allowing more margin violations or less? I forget how it goes.
it's the kind of it's the kind of budgeting for wrongly classification. So if you increase the C, it would be more.
You would
More,
allow
yeah.
more margin violations. Right. And so let's see, if you're underfitting, you want to be more strict about margin violations, right? So you would want to decrease C, I think. You want to decrease C to be more strict.
so if you see the figure number 511 that I was talking about, on top of that figure, this says that to tackle nonlinear regression task, you can use a kernelized SVM model. Figure 511 shows the SVM regression on a random quadratic training set using a second degree polynomial kernel. There's a little regularization on the left plot, a large Z value, and much more regularization on the right plot, a small C value.
I don't really see that. I mean, you know, they look the same. They look similar.
That's a fact.
Yeah, but I don't know which one. I mean, I don't see a lot of margin violations in either case.
Yeah,
So
but
it's not clear what the C is doing. But he describes what the C does somewhere. So
yeah.
um, um,
Top of the picture only he describes the thing. So C is related to the regularization. A large C value means a little regularization, and a small C value means a more regularization.
oh, okay. So large C means large penalty for margin violation. And so if you make C small, that means you allow lots of margin violations. So what we want to do is we want to go towards overfitting. So we want to increase C and be more strict about margin violations, right?
Right, right.
So we want to increase both C and gamma.
Yeah. Well, what does he mean by little regularization or more regularization? How does he define it?
Remember, regularization is a term that gets added to the loss function, and C is the scaling factor in front of that term. So regularization in this case would be the amount of margin violations, but C scales it. And so if you increase the scaling factor on the regularization, that means you're being more. That means you're really emphasizing on the regularization. So,
well, he actually said the opposite. A large C value means little regularization.
oh, okay.
Yeah. So when we are actually increasing the C value, we are sort of widening the pillar width. We are allowing more things to be wrongly classified or misclassified. Large C relates to less regularization. It's the vice versa. That's what I was about to
Large
browse.
C is a less regularization.
Basically,
Right, and that's
C
exactly what we want to do. We want to back off the regularization, right?
Right. So we allow more. So in this case, the little regularization means more margin violations and a large C value.
I mean, to put it in a crude way, I mean, regularization and the value of the C are inversely proportional here.
So if we want to decrease the amount of regularization, that means we need to increase C.
Right.
So here regularization, does it mean the width of the road, width of the street? That's what it means, right?
It means the penalty for margin violations.
So when the margin violation in turn depends on the width of the street.
Yes.
So it is directly affecting the width of the street, the regularization.
That's on 162. He exactly said that the width of the street is controlled by a hyperparameter. I think he used epsilon here, but I think it's just gamma, right?
I'm not sure. What is it? Does he ever relate epsilon to C?
On page 162, at the bottom, he said the width of the street is controlled by a hyperparameter. I don't know how to pronounce it.
Epsilon.
Epsilon, right?
Yeah.
Yeah.
But is epsilon actually a parameter that you can control from within sklearn, or?
Right.
Yeah, you
So
can control it.
Actually, in the figure 510, he actually depicts it on the picture itself as epsilon on the left hand side, epsilon as the width of the street.
Yeah.
Yeah.
Can someone share the screen or?
I don't have the book in PDF.
Okay, I'm sharing the screen.
Thanks.
Yes, so I guess you guys can see my screen. So on the left hand side, he says this one, this associated text. He says the width of the street is controlled by a hyperparameter epsilon. Figure shows two linear SVM regression model trained on some linear data, one with a large margin where epsilon 1.5 and other with a small margin epsilon 0.5. So here this is the point he makes, that epsilon is the width of the street. So in that case, adding more training instances within the margin does not affect the model prediction. Thus the model is said epsilon insensitive.
Right.
So epsilon dictates the width of the street. So in that case, C dictates, as Joseph was saying, the penalty that is associated with a misclassification. But
The
that by
way
definition,
I used to remember is C is inverse. Typically, in a linear non-SVM case, you use kind of alpha as the weighting parameter for your loss. And in case of SVM, because if you go into the detail of the math, the multiplying parameter shifts to the first value. But ignoring that, the simplification that I use rule of thumb is C is inversely proportional to, the way to think of it is C and alpha are inversely related to each other. So higher C is like having a large alpha and vice versa. So, or smaller C is equivalent to having a large alpha, sorry. So that's why C is, so if you remember that, then a high C is low regularization, a low C is high regularization.
Srinivas, alpha, you mean alpha epsilon, you mean here, right?
No, none of these. It's just a regular, when we
Okay.
did the linear equation, then it's the constant, or not constant, but it's the value by which you scale the L2 square or L1
Right.
parameter. So it's what Joseph was
Alpha,
explaining earlier, that the
alpha by 2
weight
is
that you
alpha.
apply to the regularization parameter in the loss function.
So intuitively, if we think about it, the epsilon is, as he directly saying, it dictates the width of the street. My point is that now C, as we understand C, the effect of C, it also dictates the loss. And the loss is associated again with the width of the street. So isn't it indirectly again dictating the width of the street? So both of these things, aren't they doing the same thing?
No, because the width of the street is independent of whether or not you're allowing margin violations. And that's what C is related to, whether you're allowing margin violation, how much penalty you're imposing for margin violations.
Okay.
So if you put C small, that means there's little penalty for margin violations. And so you're going, let's see,
No, that's the way.
yeah, it's the other
Small
way, but I
c,
don't understand it. Because if
the,
you look at equation 5.4 on page 167, or if you have the Kindle version, it's right above the section on quadratic programming. It's right above there. And you can see the equation. You're trying to minimize the weight, the squares of the weights plus the C term, C times the sum of all the slack. But I think it's what Srinivas said is right, is that increasing C decreases regularization. It's just that I don't see how that works. But in any case, for this problem, we want to decrease, the general idea is we want to decrease regularization, right? Because we're underfitting. If we were overfitting, we would want more regularization to control it. So, gamma and C both have to go in the direction that makes less regularization. And so they would both, if Srinivas's understanding of C is correct, then we would have to increase C, and I already explained why I would have to increase gamma. So now Wenchang can tell us what the right answer is, and we can see.
Yeah. So the right answer is yes. So in his definition, too much regularization actually just you're underfitting, and to decrease the amount of regularization, which means you want to reduce underfitting or increase your variance. So when you want to increase your variance, you need to increase gamma or C. That's the answer.
Okay, does everybody understand why we have to increase gamma? I tried to explain it, but I'm not sure I did a very good job.
Yeah, so I mean, that's, he said exactly on page 167, right? So right up on top of that equation, he said, now we have two conflicting objectives. Make the slack variable as small as possible to reduce the margin violations, and make half of W transpose dot product W as small as possible to increase the margin. So when you have the left part of the equation to be as small as possible, that actually increases the margin. So which means when you increase the margin, and sorry, to make the left part of the equation as small as possible, you need to increase C, right? Because overall you want to minimize the entire equation. And
Avanjit, share your screen and show us where you're seeing it.
yeah, well, can somebody share the screen?
Let's see.
Yeah, of the PDF.
Yeah, if you're following along in the Kindle version, it's right above the section on quadratic programming. And if you have the hardback, or the text version, then it's on page 167, equation 5-4.
Mm-hmm. Right, and if someone wants to share the PDF or share the screen, because I only have the physical book.
Okay, I can do that as soon as I find the sharing place. Let's see. Hold on for a sec. Here we go. Okay, I'll share my screen. Let's see. Okay, I've got the. Okay, I just have to go back to the right place. Clicking through under the hood. Okay, I missed it. Let's see. Yeah, yeah. It's on the lower right of. Sorry, I just moved away from it. Hold on, let me get back.
Right. So.
Okay, now it's on the lower left of what I'm sharing,
Okay.
right?
Yeah, so it says right here, now we now have two conflicting objectives. Make the slack variables as small as possible to reduce the margin violations, and make half of WTW as small as possible to increase the margin. So when you have a small, basically what he's saying, when you have a small half of W transpose times W, that actually increases margin. And how do we have a small left side equation, basically under equation 5-4, minimizing this equation, this entire equation? So how do we have a small half of WT times W, which that is 2, actually increase C, right? Because you want to minimize the entire thing, and when you increase C, then you have a smaller left side equation. And when you which means when you increase C, you increase the margin, and which will increase the margin violations, which would reduce the underfitting or bias, and will increase the variance. So that's the answer right here. Anyone else has any questions?
C is a multiplier of the slack variables, which it seems like if you make C large, that means you're penalizing margin violations. But that's the opposite of how it seems to work.
What? But he says right here, right? Make the left side equation as small as possible. That's how you do it.
Make the slack variables as small as possible to reduce the margin violations and make. So he's saying make them both small.
Oh, you're saying the slack variable also kind of conflicts. Well, I guess that's what he said. It's a little conflicting here.
Yeah, I mean, C has to do with the penalty for having margin violations. So it seems like if you increase C, then you're increasing regularization, but that's wrong. So I don't understand it.
Hmm. I think he said this is where the C hyperparameter comes in. It allows us to define the trade-off between these two objectives.
Mm-hmm.
Yeah, because when you increase C, obviously the slack variable will probably go smaller, but also the left side of the equation will also go smaller. So, and also it's subject to T times that larger equal to 1 minus slack variable. Okay.
Oh, I think what you said makes sense. So if you increase C, you're forcing the sum to be, you're minimizing the whole thing, and if you give it a larger value of C, that means it has to make the sum smaller, the sum of the slacks smaller, and that means less margin violation, right?
You actually no, you actually want more margin violations, so it's still conflicting.
No. I mean, if you make C large, that means you have to trade off by making the sum of the zetas, the sum of the slacks, small. And so it's in some sense telling you that you can't have, if you want to minimize this whole thing, the slack variables have to be small, which means that when you drive up C, you're driving down the margin violations.
Yeah.
I think that's what makes sense.
Yeah.
Yeah, because the bigger C is, the more it costs you to have a margin violation. So you're going to want to minimize those. So Wencheng, you led me to the answer there. So I think it's what you said that made me think of that. So yeah.
Joseph, that should not be a generalized blanket statement, right? We have to always try to hit the sweet spot between overfitting and underfitting, right? I'm just trying to understand, make sure that people don't take your statement with absolute, as an absolute one. So increasing or decreasing this C value without checking the underfitting or overfitting doesn't make sense.
No. It's just in the context of this answer, of this problem, and the general observation is that increasing C makes you have less margin violation. It forces you to have less margin violation, and so
Okay, well, let's keep going. Maybe we can find a better answer.
So it's what Srinivas said, is that increasing C makes you have less regularization. That's consistent with decreasing the sum of the slack variable.
Correct.
So it is a general statement that increasing C means less regularization. That's what Srinivas said in the first place.
Yes. But when you say decreasing the regularization or increasing the variance, do you mean more margin violations or wider margin?
Well, both things come into play, right?
or less. So my question is, when we say less regularization, do we mean more margin violations?
Less regular. Okay. Margin. So what is regularization? Regularization is reducing the constraint. Is reducing the hard constraint of the least squares problem, right? It's making this. It's allowing the solution to be more sloppy than the optimal solution, right? And so that means wider streets. You're allowing more. You're allowing. Sorry. That means, let's see, in the context of wider or narrower streets. It means narrower streets, right? If you have wider streets, that's harder to get. That's harder to achieve.
Right.
So
Yeah.
narrower
Okay.
streets would be in the direction of less. Sorry, narrower streets would be more regularization, and
Yeah.
allowing margin violations is also more regularization. I mean, if you allow lots of margin violations, then you're allowing sloppy, you're allowing a very sloppy solution, and so that's regularizing. That's a regularizing thing, right?
Right. So I guess in this scenario, in this case, basically less regularization would be more variance, and more variance actually in this case means just actually narrow street rather than wider street. So I got that wrong, I guess. More variance actually means
narrower street.
Yeah,
Yeah,
you want to be as accurate as possible, and so
yeah. You want to force the thing to be as closer to the real optimal solution. The one imposed
accuracy.
by.
Yeah. Okay. Well, great. That was great. How should you? So number 7. How should you set the QP or quadratic programming parameters H, F, A, and B to solve the soft margin linear SVM classifier problem using an off-the-shelf QP solver or quadratic programming solver?
So where does he talk about that? Oh, there it is. Okay, so this is on page 168. If you have the book, or it's near the dual problem section if you have the Kindle. So that's how to navigate to it. I bought it here so I can navigate to it. Let's see. So it's near the dual problem. So I think it's on the other. It's closer. Okay, there. So on the right side there, that's the. This is how a quadratic problem. This is the general formulation of a quadratic programming problem, right? And they have off-the-shelf solvers that can deal with them, right? So now he says we have a linear problem, and what are the conditions? He says we now have a linear problem, and we want to know how to set all those parameters. And we have a soft margin. We want to allow a soft margin. So let's see if it's a linear problem, then let's see. P is an N. I think H is the identity here because let's see. I mean, the problem looks like the one we just looked at, 1/2 W transpose W plus the sum of some slack variables. CP. Subject to. Okay, so we have 1/2 W transpose W. That's what we have to minimize, and so we don't have, and we have to minimize it subject to some constraints. I think the constraints are where the slack comes in. Let's see if you. I guess if we look at there's a page where it shows how the problem looks, how the loss function looks. I want to navigate to that. Let's let's see, goes on the online problem. Online SVM. So here's what the loss function looks like. Let's see, so there's the W transpose W, and then we have this max of W transpose X plus B. That looks similar. The H is the identity. That's the first thing we can notice. The sum from I equals 1 to M of this stuff. We don't. How do we express the constraints in this problem? Okay, this is the dual form. Let's go back to the primal form. Okay, so this is it here above the quadratic programming section. This is the soft margin linear SVM classifier. So this is what we have to deal with. So let's see, F transpose P. I don't see how to. So I see W transpose W there as P transpose P, but I don't see it. I don't see P appearing. P is the weights. P is the weights W, and I don't see them appearing here. Something else. Subject to AP less than or equal to B. And that would be this equation. AP.
So definitely each should be an identity matrix.
AP, well, it's the AP less than B inequality. That's a set of inequalities. And that should be this equation here, which has I terms in it, right? For I equals, it has M terms in it, right? And so presumably we can figure out what A is by writing it all out. We'd have to move the zetas on one side, and we'd have to move the beta on the B on the other side. All the constants are on the right-hand side, so we would have B and 1 on one side, and all of the other stuff is on the right-hand side. So we would. B is a constant. It's basically we have to massage this equation, this inequality, to make it look like that. So each row of A is going to be, so if P is the weight vectors, and then each row of A is going to multiply, P is the column vector for the weights, and each row of A gives you a linear combination of weights. What's X in this equation? X. I think it's the data. I think it's the data point. Yeah, I don't see how to make, so obviously this, the the target for minimization is this part, you know, the W transpose W plus the C term, and that should be massaged to make it look like this. But I don't see how to do that because if P is the weights don't occur in a linear sense. They only occur in a quadratic sense. So you'd have to make the F's 0. But if you made the F's 0, you wouldn't have this term. So this is a little W is the weights. So W is an m-dimensional. W is an m-dimensional vector, right? I think. I think we could add something to W. If W is a dot product, then we can redefine W to be something like W plus the square root of C times the square root of gamma. Oh, sorry, square root of zeta. And then if you square W, if you redefine W that way, let me see if I can do this with a, somebody stop me if you think I'm wrong, but I'm just gonna proceed here and see what to do here. I'm just saying, let's redefine W, make it W prime equal, and W prime, let's look at the ith component of W prime. Let's make it the ith component of W, and then we add, just for fun, we add this term, square root of C. Sorry, I don't like that. How can I erase it? I better not start with erasing because then I won't be able to. Okay, so square root of C times square root of slack. And the zeta is, remember the zetas are, it says that the zetas are positive, so we're allowed to take their square root. So if I do that, this is a zeta sub I, right? If I redefine W that way, then I can write W prime transpose W, that is W prime transpose times W prime with the 1/2 in front of it. You see what I'm doing, right? I'm going to make this term look like this term. And now when you take the dot product, it's going to be, no, that's not going to work, is it? W, yeah, it will. It will be W I plus plus the square root of C times the square root of zeta I times, and so it's going to be this thing transpose times itself. But that's not going to work. Sorry, that's wrong because it.
Yeah.
There's this cross term. There's cross terms that I can't get rid of that way. So sorry, that's not going to work.
So let me just read the answer for the sake of time, and perhaps we can, you know, think more about it later on. So the answer is, let's call the quadratic programming parameters for the hard margin problem H, F, A, and B. And he said C quadratic programming on page 167. The quadratic programming parameters for the soft margin problem have m additional parameters. So NP actually equals to n plus 1 plus m and m additional constraints. parenthesis, and C equals 2M, close parenthesis. They can be defined like so. H is equal to H prime plus M columns of zeros on the right and M rows of zeros at the bottom. And there's basically a matrix that's defined here. F is equal to F prime with M additional elements, all equal to the value of hyperparameter C. B is equal to B prime with M additional elements, all equal to 0. A is equal to A prime with an extra M times M identity matrix IM appended to the right. I think it's IM just below it, and the rest fill with zeros. And he defined the A matrix with A prime in the answer. To be honest, I didn't understand too much of it.
NC is N constraints and NP is N parameters, right? Yeah. Yeah, I didn't follow much of that either. So he's saying that given the hard margin solution, you can describe the soft margin solution in terms of it, right?
Right.
Okay, but it's not clear how you even get the hard margin solution. So, yeah.
Yeah. All right. Well, we just have to kind of just continue to go forward, and we can probably think more about it or Google around. Maybe someone asked a question. Cool. So now we're left with 8, 9, 10, and we got half an hour. So I want to see if we can at least do one of the 3 problems, and let's see. So number 8, I think it's just he kind of just did it with iris data set, and number 9 is MNIST, and basically he's asking you to train one versus the rest to classify all digits. And number 10 is train an SVM regressor on the California housing data set. I guess pick one.
Yeah, why don't we just do one? Why don't you? I'll give you the screen back, and then you can. Do you have a Jupyter Notebook open, or?
Yeah, I do.
Okay, I'll just give you the screen back, and then you can take over, and we can just sort of try to do this together.
Yeah.
Whichever one we pick. So, let's see. Data set.
So I have it right here.
We can do the iris. That's 8, right? We can use the iris data set,
Yep.
and you do number 8.
Yep. So iris data set. I mean, it's fairly straightforward, right? I mean, even though the mathematics were really heavy, but like you're literally just calling like SVC right here, a linear SVC or SG classifier.
But hang on, there was something that I thought was interesting right where he does this. After spending a lot of time in the books telling us to use, primal, or, the dual is false when M is greater than N, I was surprised that he used the default where I think dual is true, if I'm not mistaken. So I tried using dual is false with the linear
SVC.
CLF, the linear CLF with dual. And if you say dual is false, it actually fails. And you learn something by doing that, because what happens is the dual is false doesn't work with losses hinge, which is what he specifies, right? So, and you find out that the default loss is hinge squared, and that, so if you use dual is false, then you need to let the loss be the default, which is hinge squared, as opposed to the primal, in which he uses. So my point is, feel free to play with these things because you learn more by doing that. You know, so I was curious why he's, first of all, you know, based on what we just discussed, he was telling us that when m is greater than n, then you'll you know, go the other way, which is that primal will work better. So I was like, why are you sticking with why are you not doing that? And in the process found out that, you know, the losses and other stuff in default is it doesn't work, and so you have to let it, the loss be default, which is not hinge but hinge squared.
So you're saying, Srinivas, that the default behavior of the classifier that he defined there is defaulting to the dual problem?
I believe that dual is true for default when you do the
Hinge, when the loss
linear
is hinge?
CLF.
Oh. Linear classifier always gives you dual equals true, is that what you're saying?
Yeah, I believe so. You can try it by just specifying that in that box and seeing what it does. But
we can check on the API directly. So it actually says that dual is equals to false when n samples greater than n features.
yeah, and
So
in
it
this
automatically,
case,
it automatically uses primal for this problem then, right? Or...
yeah, I was just playing with it to see what happens if you say dual is false, and with dual equals false, if you specify loss as hinge, then it doesn't work.
The dual parameter is on the top. Go to the top.
Yeah.
The third one, the third parameter.
The dual is true, right, over there. So
default is true, right? So
yeah,
right here.
The default is true. So since the default is true, and we want the default, I mean, we want the dual to be false based on what he told us, right? That we want the primal if m is greater than n, because it's skinny, as Joseph explained. When it's skinny, we want the primal, not the dual. Right? And so that's why I went and switched it, saying, hey, I want it faster. Why do I want it slower? You just told us that's faster, so but that doesn't work.
And also you have a linear problem, so you wouldn't think you need a kernel. You don't need a kernel trick.
Yeah, exactly. So he doesn't use kernels in any. So I did that, and in the process found out that, oh wait, dual equals false doesn't work with losses, hinge, and L2 regularization. So when dual is false, then you leave the loss has hinge squared, which is the default, by the way.
Ah, okay. And
so you're just saying basically if it's primal, then we need to use square hinge. We have to use square hinge, otherwise.
Yeah, which is the default. So if it's primal, you know, just say C is C and random state. Don't define loss, and then it works. So I added a line the classifiers. Instead of 3 classifiers, I did it with 4, just so that I could play with one more to see what happens when I have dual is false. So.
And did it do better? Did the primal do better than the dual then in that case?
It was all about the same, but what is interesting, and I haven't quite figured out the answer to that, when it came to plotting, it was unable to plot the line for the dual. Don't quite understand why, because I just followed it, and it gives me the numbers, but it doesn't plot it. So I don't know whether it's shifting the parameters when I go to dual or what.
Can you tell me the exact error? Maybe I can Google it.
No, it doesn't give an error. It just simply doesn't plot.
Okay.
So I mean, it's, you know, if you go through the rest of the cells, you'll see that in one cell he plots the 3 in the notebook. Back in the notebook, he plots the notebook that you had. He plots the 3 classifiers, right? He shows that they are all equivalent largely.
Wencheng, could you go back 2 clicks? Because I saw something on the screen before you went to this page that said, you just go back twice. One more. Okay, see, how is hinge loss related to primal dual form? That's the question that Srinivas brought up. Straight from the hinge loss.
I think hinge loss squared has to do with L2. That's what the other post said.
Yeah, which is why the hinge squared, when you, or since hinge squared is the default, you don't specify anything and you say dual is false, then for the primal everything works. But if you don't do that and you try to specify hinge loss for primal, then that doesn't work with L2 regularization.
So it means if it's linear or primal, you have to use L2 instead of L1. That's what, yeah, that's basically what it means, right?
Well, hinge loss is the second of the inequalities, right?
All right. I mean, do we want to take on just that? The number 8, the iris. I mean, we can start playing around and just do that. If you guys want to pick this one, and just since we have questions, so we might as well just dive into it.
Sure.
Okay. So let's do this, and we should probably stop around in 15 minutes, then we can discuss. So maybe another 15 minutes, and I'll call it a stop, and we'll discuss. Okay.
All right. So we're all having a look at problem 8, problem 8 then?
Yeah, let's do that. Okay, I think time is up. So let me share my screen. I guess the question is actually quite straightforward. You're basically just testing, well, trying to build SVM classifier from three different classes. But with the last one, that's a little more complex in terms of the parameters. And I think so you actually don't have C from SGD classifier, but you have alpha. And I was looking up on this alpha why he calculated it this way, and it turns out I found this. Basically, someone asked it, how does alpha relate to C in scikit-learn's SGD classifier? And the answer, the correct scaling is CSVC times n samples, which is the number of rows, equals to 1 divided by alpha SGD instead of that. And so that's actually how he calculates it. If you see it, it's basically alpha equals to 1 divided by C times length of X. And what's interesting here is this guy or gal was saying basically, after a quick overview, it seems that equivalence is CSVR is more so equivalent to that CSVC and C logistic. And it was also saying basically the alphas are roughly equivalent. So pretty interesting. So I guess back to the point, so you don't have C here, but you can do alpha, and you can calculate alpha from C. Cool. And I think in the end, these two, I think intercepts and coefficients are roughly the same. And but somehow this is a little different. I haven't got the time to interpret why that is. Anyone has any thoughts on that? Does anyone want to say anything? No. Okay. Well, and also like
actually, sorry,
yeah.
I did get, while using different parameters though than what he used, specifically on, instead of using constant learning rate, if you do learning rate optimal, then and same alpha and everything, then the value you'll see of the SDDC is a lot closer to what you see in the others.
Let's try that. You said optimal?
Yeah, and get rid of the eta because that's only for constant.
Okay, so constant. Just comment this out, and you said get rid of ETA.
Yeah.
Okay. Interesting. And let's see what this means optimal.
That's the default, and it's the optimal learning rate that it figures out rather than the constant that you supply.
Yeah.
I think it is that point where as you approach the minima, then it changes the learning rate. It reduces the learning rate. Maybe that one.
I think it's
Yeah, it's
1
learning rate
divided by.
annealing that it's applying, very rudimentary learning rate annealing.
Hmm.
So, okay. So it's more like scheduling learning rates and stuff.
Yeah, in fact, if you can see the value, and if you plug in the appropriate value, then it just reduces slowly as you go further, as you will.
Yeah, it says as long as the training keeps decreasing, decrease. Okay. Got it. Cool. And what's initial learning? Oh, so this is the initial learning rate basically for the constant. Okay.
I have a question here. So, is it possible to find out this learning rate? As a matter of fact, other parameter as well using grid search CV, or is there any limitation of that? That only these things you can find using grid search.
Yeah, you can actually. It's we did that in chapter 3 exercise. You can search bunch of gamma, C, and learning rates with grid search CV. Yeah, you can.
So it is not related. It is not restricted to searching only integer value or float value like numeric value. You can search for other parameters like learning rate as well. Say for example, there are a bunch of parameters here
Yeah.
like constant and optimal. You can search those as well, right?
Yeah, so let me just show you really quick. 1 second. It's taking a little time to load. I think the notebook is a little big. Okay, let me scroll down all the way. Just research CV. No. Um,
I think here only.
yeah, this is Kenya's neighbors. Oh, it might be chapter 2. 1 second. It's probably chapter 2. Memory got crossed. Okay. Right here. So you can search C and gamma, but I guess you didn't search what it was. Let me just go through the solutions actually. Yeah, so you can search kernels. You can do linear RBF. You can do C. You can do gamma. I'm sure you can do learning rates as well. So
Okay.
yeah,
Oh.
and yeah, and you just call grid search CV, and you just instantiate it as VR here and you feed it in. That's it.
Okay, that's great.
Yeah, yeah. Okay. I mean, even though I think this didn't turn out to be close, the third one, but somehow the line is still very close. He said close enough right here. So I still have to kind of just dig into how these are interpreted.
So I have a question here now
Yeah.
regarding this plotting. If you go through other notebook that he provide along the chapter, the general way that he does is that for this kind of linear plot, he comes up with a line space, numpy dot line space. On top of that, he takes this as the input data. Then on the trained classifier, he does that say linear regression dot predict. Then he provides that line space value, takes the output and prints that. But here he is going through this inverse and all this mathematical stuff. So what exactly he is doing here?
Yeah, I had some questions on that as well. He said basically transform the decision boundary lines back to the original scale. Basically, I guess we probably scaled this with the standard scalar, and he wants to scale them back.
So
That's my take.
okay, so is it something like that he can't apply the line space thing directly here because it is the standard scalar has been applied? That's why. So if we do it that way, if we take the line space and we apply the standard scalar on that as well.
Subhashish, can you tell me which page this problem, the question you're asking is on?
It's on the screen. The line, the code that
Oh, okay.
when
Okay,
they
sorry, I'm not, there we go. Okay, I had the screen blocked, sorry. Okay.
So here, generally, the general trend is that if you see the plot, there is a plot beneath. So if you see the general way he plots this kind of thing, he does is that he comes up with there are two ways. If he wants to plot this kind of thing, he comes up with a line space, takes that as an input, then passes that as input to the learned or the trained model, then takes out the predicted output, then he plots that. Or if he wants to plot a decision function, then he goes for a mesh grid. That's a generalization. But here if you see, he is plotting the thing in some other way, taking inverse transform and all. So why is he doing this way for this particular case?
I think he's transforming he does the scalar inverse transform. So so you've scaled all the data, right? And then he's reconverting it to the original petal length, petal width kind of stuff by applying an inverse transform, which is like, for those familiar with fast AI, it's like applying decode instead of encode. So he just is re-getting the actual values rather than the transform scaled values. And he's going back and then plotting it on that so that you can see with respect to the original scale rather than the scaled values.
So Srinivas, if we see if you see the line, then he is actually doing on -10 to +10, something like that. So can we take it this way that he is actually working on a -10 to +10 scale, only that he is inverse transforming so that he can fit into the scalar.
Yeah, that may be yes. So this -10 +10 multiplication, division, or addition that he does, maybe like you said, to kind of put it in all in the same scale.
Scale, right.
But my answer had to do more with the inverse transform is since we have transformed the data by scaling it, he's taking it back to the original. So you can otherwise he can't say petal length and petal width because now we have normalized, right? We have scaled.
Right. Right.
So he's doing that in order to plot it to the original dimensions. Now, the -10 and all that is scaling, arranging it, as you say, to get a nice chart. But the important thing to realize is he's flipping it back to the original thing because we have scaled.
Right.
Yeah, and if you, I mean, we can literally see as X scaled what it looks like. So it's all like basically, yeah, so basically almost like within -2 and
Yes, so scaling means
+2.
plus 1.
Yeah, and let's see what line 1 looks like. Oh, I didn't.
Run that.
Oh, I didn't import.
You can run the very first one.
I don't think I import.
No, it's not there. If you need to run either, you need to type or run the first cell.
Yeah. There you go. Okay, so that's what it looks like. 9, 2, 9, 3. Okay. And what does X looks like? Yeah, so it's basically back to sort of a scale of X. X was transformed into a range like this, but originally it was like this, and now it's kind of back to that, but also like just, but he also used -10 and +10.
Yes, so basically if you see the where you plotted the line 1, line 2, line 3, those value are basically coordinates. So x1, x2, he is plotting, taking the 2 coordinates there and plotting it there. If you see
Right.
the value of line 1, line 2, it is just 2 points.
Yeah.
So he is basically, instead of taking it directly as a line space, he is just inverse transforming it to the plane. Then taking that transformed coordinate and then plotting that one.
Right. Okay. Well, we should probably stop because we're 15 minutes past the set schedule. Does anyone want to make any additional comments or before we wrap it up?
So in the next session, are we going through the chapter 6 notebook? I mean homework?
Yes. Yes. So, yeah, absolutely. So again, I think, you know, some of the hosts don't go through notebooks, so it's actually helpful when we actually go through the exercise to get some sense of the code and also code it through yourself. So we'll go through that on Sunday. We'll not skip a session on Sunday. We'll go through chapter 6 on Sunday afternoon for the homework. So.